Today we are going to learn about the measuring methods of geometric tolerances. Why inspection is very important? There is a clear design intent from dimension tolerancing mentioned in the drawings that sets the acceptable variation a part can have. To ensure that, we should have one proof. That proof should come from inspection that confirms manufactured features match the intended geometric requirements. It improves the better outcomes in the production. So reliable checks improve fit, performance and consistency across every build. The flatness variation. What flatness checks? It confirms a surface stays within a uniform, allowable flat zone. This prevents rocking, gaps, and uneven load transfer in surface. Where it is used, ceiling faces rely on flatness to maintain consistent contact pressure. The mounting pads and reference surfaces need flatness for stable alignment. Why it matters? Better flatness improves repeatable assembly and reduces fit issues. It supports predictable performance when parts clamp, seal or slide. Flatness inspection. The definition. The surface is flat within a tolerance zone consisting of two parallel planes 0.05 mm apart. Inspection setup. Place the part on a stable surface plate, impressing the perfect plane. Representing the perfect plane. Support the part at all required points without rocking. Sweep the indicator across the entire surface. Total indicator reading TAR must be less than or equal to 0.05 mm. So flatness control frame example is given. Surface plate that is perfect plane and tolerance zone for flatness is here, and this 0.05. The entire surface must lie between two parallel planes 0.05 mm apart. The key points here: no datums are required. The surface must be within two parallel planes applicable to any individual surface. And what is parallelism inspection? In the same setup with the same arrangement, we can do this parallelism check also. That's why I've presented those two inspection or measuring methods in one slide. The definition of a surface, parallelism: a surface is parallel to a datum plane. Here datum is referenced within a tolerance zone consisting of two parallel planes 0.05 mm apart that are parallel to the datum plane. Inspection setup: establish the datum plane A, the surface plate. Here the datum plane A, the surface plate, that is perfect plane. Place the part on datum A using proper supports. Sweep the indicator across the entire controlled surface. The total indicator reading must be less than or equal to 0.05 mm. This feature control frame example: the parallelism of a 0.05 mm tolerance with reference to A. Okay, and tolerance zone parallelism The entire surface must lie between two parallel planes 0.05 mm apart that are parallel to datum plane A. So the parallelism is related to orientation, so it requires datum reference. The tolerance zone is parallel to the datum plane, controls orientation. Parallelism, not form alone, it controls the orientation. Straightness check. What straightness confirms? It verifies a line stays even without bows, waves, or local bends. It focuses on shape along a length, not overall location, where it is commonly applied shafts and pins, where smooth rotation depends on a true axis, edges and guide surfaces, where sliding contact must remain stable. Why it matters in assembly? Reduces binding, rocking, and uneven wear during rotation, motion, or seating. Improves fit and repeatability when parts must align consistently. Straightness inspection. The straightness definition as per ASME Y 14.5 mm. Straightness is a form control that limits the variation of points along a line element or the median line of a feature so that they lie within a tolerance zone consisting of two parallel straight lines in 2D or two parallel planes in 3D. Symbol, it's like a straight line for straightness. The inspection setup, the part is mounted on a rotary table to allow 360-degree rotation. The dial indicator on height gauge is set to a reference height. Rotate the table and move the gauge along the length of the part. The indicator records the variation from the straight reference line. Okay, an example on drawing, this is straightness of 0.05 mm tolerance means the median line of the cylindrical surface must lie within two parallel planes 0.05 mm apart along the entire length. Examples, for example, if I have 5 shafts of different length and it gives me different tolerances, if any of the tolerances is more than or higher than the 0.05 mm, that fail to pass the inspection. Rest all equal to or less than 0.05 mm as per the tolerance indicated in the drawing is passes the inspection. So the good part versus out of tolerance part. All the points within the tolerance zone, but the out of tolerance points, 1 or 2 points, if it lies outside the tolerance zone, then that is rejected. Okay. And measuring circularity. What circularity confirms? It checks how closely a feature's cross section matches a true circle. It focuses on shape quality, not the feature's location. Where it matters most, it is critical for holes, pins, and other round fits. It supports smooth rotation in bearings and rotating components. Why it improves performance? Better circularity reduces wobble, vibration, and uneven contact. It improves balance, fit consistency and overall operating smoothness. Circularity inspection. The definition, circularity or roundness controls the form of a feature of revolution in any cross section. The entire surface must lie between two concentric circles separated by the tolerance value. Engineering example, the cylinder bore, and there is a piston diameter, then there is an oil seal. Assembly uses O-ring as a seal between piston and cylinder. O-ring vendor states their material can fit a 0.05 mm maximum gap. Then 0.25 mm circularity tolerance could be applied to the cylinder bore on the bottom of the O-ring groove. Inspection process. Mount the part on a rotary table. The step number 2, position the dial indicator for electronic probe perpendicular to the surface at the desired cross section. Rotate the part 360 degrees and record the indicator readings. The circularity error is the difference between the maximum and minimum readings in the dial gauge. And polar graph. If an electronic probe is used, the circularity surface variation can be plotted on a round piece of paper called polar graph. The tolerance and example values. Tolerance zone, the two concentric circles separated by the tolerance value. And the cylinder bore, I have the example values, the cylinder bore, piston and O-ring. And everything, if it is within this tolerance zone allowed, then that part is accepted. The entire cross section must lie between two concentric circles at 0.05 mm apart. Acceptance, the maximum reading minus minimum reading should be less than or equal to tolerance value. Circularity versus cylindricity. Circularity 2D cross-section checks. It confirms each slice stays close to a true circle. Flags out of round conditions that affect fit and smooth motion. Cylindricity is a full 3D surface check. Verifies the entire cylinder surface is uniformly controlled. Combines roundness with straightness along the feature length. Why both matters together? They improve reliability for tight tolerance cylindrical parts. And cylindricity inspection. The definition, cylindricity controls the form of a cylindrical surface. The entire surface must lie between two concentric cylinders separated by the tolerance value. The engineering example here is, this is a cylindricity of a 0.05 mm. This is a cylindricity of 0.05 mm. Okay, the feature control frame specify the cylindricity tolerance of 0.05 mm. The entire cylindrical surface must lie within two concentric cylinders 0.05 mm apart. The inspection process, mount the part between centers or V-block fixture and support the free end. Align the part so that the indicator is perpendicular to the axis at the section to be checked. Rotate the part 360 degrees and record the maximum and minimum indicator readings. Move the indicator axially to cover the full length of the cylindrical surface and repeat. Cylindrical error here is, cylindricity error here is equal to maximum reading minus minimum reading at each cross section. Okay. and angularity control. So far we have done form checks. Now we are going to check orientation controls. What angularity verifies? It confirms a feature sits at the specified angle to a reference. So here we are going to use a reference datums. It applies to surfaces, edges, and axes that must be oriented. When it matters most, use it when angled faces drive fit, motion, or sealing contact. It prevents misalignment that can cause uneven wear or binding. Practical benefit: consistent angles protect assembly, alignment, and functional performance. Angularity tolerance inspection. Principle: a sine bar or sine plate is used to orient the control surface at the basic angle to the datum plane. The variation from the basic angle is measured. By aligning a standard angle theta we know, and the length of the sine plate we know, and then we have that height calculated from this formula h sine theta. So inspection procedure: set up the sine plate with the gauge blocks to the basic angle theta, maybe 30, 45 degrees, whatever it is. Place the workpiece on the sine plate. Bring the indicator stylus in contact with the controlled surface. Traverse the indicator across the surface. The total indicator reading must be less than or equal to the specified tolerance. The feature control frame states that the angularity of this feature should be less than or equal to or within 0.05 mm tolerance with the reference to the datum A. Okay, the surface must lie between two parallel planes 0.05 mm apart, inclined at the basic angle to datum. Okay, the entire surface must lie within the two parallel planes. Okay, that's what's shown here. Parallelism tolerance. The parallelism definition: parallelism controls the orientation of a feature so that it is parallel to a datum feature within a specified tolerance zone. The inspection process or inspection setup: use a dial indicator perpendicular to the datum plane. Move the indicator across the surface. Total indicator reading must be less than or equal to 0.05 mm. That's the feature control frame. That feature control frame means that the entire surface must lie between two parallel planes 0.05 mm apart that are parallel to the datum plane. Okay, in the inspection procedure: place the part on the surface plate that is datum A. Ensure the part is stable and fully supported. Position the indicator probe perpendicular to the feature surface. And traverse the indicator across the entire surface. Record the total indicator reading. The total indicator reading must be less than or equal to the specified tolerance value to accept the part. Okay. Perpendicularity. The definition: perpendicularity controls the orientation of a feature so that the feature is at 90 degrees to a datum plane or axis within a specified tolerance zone. What is the inspection procedure? Place the part on the surface datum plane and ensure the part is stable and fully supported. Set up a separate square or use the indicator holder perpendicular to the datum plane. Position the dial indicator probe against the feature surface. Traverse the indicator up and down. and across, if required, record the total indicator reading. The total indicator reading must be less than or equal to the specified tolerance value. Okay? And locating true position. What position control verifies? It checks that a feature sits in the correct location from chosen datums. It protects the design intent for alignment between meeting parts. Where it is commonly used, it is applied to holes, slats, and repeated patterns on a part. It helps ensure patterns match across parts during assembly. Why it improves assembly? Accurate position reduces rework by enabling first-time fit. It lowers misalignment risk in fastened, pinned, and guided joints. What is the inspection procedure? First, the example of the position tolerance and the datum reference, datum C, datum A and B, datum you see that datum A, datum B, datum C. These are three datums. And the position tolerance zone explains what each whole axis must lie within a cylindrical tolerance zone of 0.050 tolerance at maximum material condition relative to the datum frame A and B. Okay, and inspection using CMM, a CMM probe probes each hole and calculates the position of the whole axis relative to the datum A and B. Okay, hole within tolerance zone means the actual whole axis is in green. Okay, this is what tolerance zone, 0.5 mm tolerance zone. Then actual axis is within the tolerance zone, so we will accept the part. And profile of line or profile of surface tolerance. The profile of line controls the form of a line element, edge, center line, or intersection. The actual line must lie within a tolerance zone of specified width. The center line of the tapered surface must lie entirely within the two parallel lines 0.05 mm apart, oriented to a true position by datum A. Inspection process: establish the datum, select the method, measure the actual line, and analyze that within the tolerance line. The result, if it is within the tolerance zone, then the part passes the inspection process. And profile of a surface controls the form of a surface element. The entire surface must lie within a tolerance zone of a specified width. Same process, you check and ensure that the entire surface lies within the tolerance zone. Assessing concentricity. What concentricity verifies? It confirms multiple circular features share the same center line or axis. In this picture itself, you see that in bearing also there are so many circular features. This is a different dia, this is a different dia, this is a different dia, but shares the common axis. This keeps the features center, the complete entire component center, consistent across related diameters. When it is critical, use it when one cylindrical surface must stay centered to another. Typical for hubs, sleeves, parts that rotate or locate precisely. Why it matters? Better centering supports smoother rotation and reduced imbalance in motion. It also improves alignment between meeting parts during assembly and use. The concentricity inspection. The concept is concentricity controls the relationship of the center of a feature of service to a datum axis. The center of the feature must lie within a cylindrical tolerance zone. The tolerance zone is coaxial within the datum axis. You see that concentric tolerance of cylindrical zone 0.03 mm with reference to datum A. Okay, here it means the axis of the 20 dia feature must be within a cylindrical tolerance zone of 0.03 cylindrical tolerance zone, that is concentric with the datum axis A. Okay, and the acceptance criteria. Okay, inspection setup. You see that mount the part between centers using datum A in the rotating axis. Place a dial indicator on the 20 dia surface feature. Rotate the part 360 degrees. The total indicator reading must be less than or equal to 0.03 mm. Okay, thank you. And monitoring runout. What runout checks? Runout captures surface variation as the part rotates about a datum axis. It reveals wobble or out of true motion that appears during rotation. Where it is applied, common for rotating features that must run smooth and stable. Useful when vibration, noise, or uneven contact must be minimized. Why it matters? Lower runout supports better rotational accuracy and consistent performance. Runout and total runout inspection. The runout means the variation of a surface as it rotates about a datum axis applies to one circular element or surface. And the total runout, the variation of the entire surface as it rotates about a datum axis applies to all surfaces of the feature. You see that the datum axis is rotates and we are checking the runout. And in this total runout, you see that runout, one circular element, and total runout means entire surface. We are going to check the cross-sectional area, I mean circularity, as well as the straightness. That is total runout. Here, that total runout comes from one reference dia to the other. Okay. And inspection takeaways. What the checks achieve. Each control verifies a specific aspect of geometry and form. Using the right method turns tolerances into clear pass or fail results. How to choose the right one? Select checks based on assembly fit, motion, behavior, and function. Anchor inspection to the features that matter most in use. Quality outcome. Consistent inspection reduces rework and improves manufacturing confidence. Thank you. Thank you for watching this video.